So right under your feet, right here, right now, it's not the solid ground you're used to. It's not endless layers of earth. It's not the backs of giant turtles or elephants, like you hear whispered in ancient Asian myths. And it's not some colossal pillars holding up the world like in the biblical stories. No, beneath you is the same bottomless, beckoning sky that's spread out above your head. Sounds incredible, right? Maybe even insane? Especially when you remember that 26 centuries ago, every known civilization, from the wise Egyptians and mysterious Chinese to the builders of Babylon, the peoples of ancient India, Africa, the Native Americans, and the Hebrews, all of them, to a man, saw the world differently. Heavens above, earth below, resting securely on something. All of them except for one. So how did it happen? How in one single corner of the ancient world, in the Greek polis of Miletus on the coast of modern-day Turkey, did a thought so audacious, so contrary to all accumulated human experience take root? A thought that didn't just challenge millennia of belief, but forever changed the very meaning of down. Who dared to suggest that the earth is just a rock floating in the void? Floating but not falling. And why did he succeed when everyone else was still clinging to the old familiar images? The answer to that mystery lies in the story of one man whose name was Anaximander, and our journey to that answer, to unlocking his genius, is what we're about to begin, by diving into a world where the very idea of scientific inquiry was just being born. The man who made this colossal, almost unthinkable leap in understanding the world, Anaximander of Miletus, lived 26 centuries ago. That one staggering insight alone, the earth, suspended in the void, surrounded by sky on all sides, would have been enough to etch his name forever into the pantheon of humanity's intellectual giants. But Anaximander's legacy stretches so much further. He didn't just look down at his feet and see the sky. He paved the way for physics as we know it, for geography, meteorology, even biology. But even more importantly, he kicked off a revolutionary process of rethinking our entire worldview. He initiated a search for knowledge that rejected any and all certainties, even the most obvious ones. This bold refusal of the self-evident became one of the cornerstones of scientific thought. And the nature of that scientific thinking, man, that's the second major thread we're going to pull on throughout this story. A lot of people think of science as just this collection of solid, unshakable facts, something set in stone. But what if its real power isn't in establishing those facts, but in something else entirely? What if it's about the radical, almost terrifying awareness of just how vast our own ignorance is? It's precisely this realization that we know so little that allows us to constantly question our own knowledge, our most deeply held beliefs, and in so doing, to keep learning, to keep discovering. The scientific quest isn't fueled by some ironclad certainty, but by its very absence, a radical lack of certainty. Its path is fluid, capable of continuous, almost organic evolution. In that lies its immense, almost magical power. It can tear down established orders and reinvent the world again and again, as if for the first time. This way of seeing science as something subversive, visionary, constantly in flux, is a world away from the dry philosophical treatises of the positivists or the fragmented, sometimes lifeless picture of science painted by some modern thinkers. Here, we're going to try to illuminate science from a different angle, from the perspective of its critical, almost rebellious ability to rethink the world over and over. And if that rethinking is the central feature of the scientific enterprise, then the origins of this incredible adventure aren't to be found in Newton's laws or Galileo's experiments, or even in the reflections of Francis Bacon, and definitely not in the early mathematical models of Alexandrian astronomy. No. The beginning of it all was the first great scientific revolution in human history, Anaximander's revolution. Anaximander's importance in the history of thought is, without a doubt, massively underestimated, and there are a few reasons for this. On the one hand, back in the ancient world, his contribution was recognized by authors with a scientific bent, like Pliny, whose words that Anaximander threw open the gates of nature are just full of admiration. But on the whole, ancient writers, including Aristotle himself, saw Anaximander as a proponent of a naturalistic approach to knowledge, an approach that was strongly opposed by other cultural currents and which, let's be honest, hadn't yet produced the kind of stunning results we see in modern science. The naturalistic project back then, in the 6th century BC, really hadn't had time to bear the rich fruit it would offer the world after a long process of maturation and numerous methodological adjustments. On the other hand, the reason he's underestimated today lies in the modern and frankly harmful split between the natural sciences and the humanities. As a modern scientist myself, I'm aware that my predominantly scientific training makes evaluating the contribution of a thinker who lived 26 centuries ago a risky business. But I'm convinced that most, if not all, of today's discussions about Anaximander's contribution suffer from the opposite problem. I'm talking about the difficulty that specialists in history or philosophy face when trying to assess the importance of discoveries whose significance and impact are purely scientific. It seems to me that even those authors who readily acknowledge Anaximander's greatness don't always fully grasp the sheer historical importance of his numerous insights for the development of science itself. In these pages, I'm going to try to draw attention specifically to that scientific importance. So I'll be looking at Anaximander not as a historian or a specialist in ancient Greek philosophy, but as a modern scientist trying to understand the nature of scientific thinking and its role in the long-term development of civilization. My goal isn't to challenge the painstaking reconstructions of historians like Charles Kahn, Marcel Conche, or Dirk Couprie, but rather to shed light on the depth of their thought and the colossal role that Anaximander's insights played in the development of universal knowledge. There's another, less obvious reason why Anaximander's ideas and Greek scientific propositions in general are so undervalued. It's rooted in a widespread and, in my view, mistaken understanding of some central aspects of scientific thought itself. The naive confidence in science of the 19th century, that whole celebration of science as the final word on the world, was brutally undermined. One of the main forces behind that was the revolution in 20th century physics. This revolution led to a staggering discovery. Newtonian physics, despite its enormous, time-tested effectiveness, is actually, strictly speaking, wrong. Can you imagine the shock? Much of the subsequent work in the philosophy of science can be read as a desperate attempt to cope with the disappointment this discovery caused. What exactly is scientific knowledge if it can be wrong even when it's incredibly effective? A broad current in the philosophy of science reacted to this by trying to find some unshakable foundation, a base from which confidence in science could be preserved. Scientific theories, for example, began to be interpreted as constructs whose value was limited to their directly testable consequences within given domains of truth. The knowledge contained in scientific theories was reduced to just the ability to make predictions. In doing so, I think we lose sight of the qualitative aspects of scientific knowledge, and in particular that variability of science to subvert the status quo and expand our vision of the world. These qualitative aspects are not only inseparable from scientific thinking and necessary for it to function, but more than that, they are its primary motivation and the very reason it's interesting to us at all. At the opposite end of the spectrum, another broad current in modern culture belittles scientific thinking and fosters anti-scientific sentiment. At the start of the 21st century, in many corners of the world, rational science began to be treated with suspicion, almost with hostility. In cultural circles and in everyday life, various forms of irrationalism have reared their heads again. This anti-scientism feeds on the disappointment caused by science's inability to give us a complete, final vision of the world. It feeds on the fear of accepting our own ignorance. False certainty, however shaky, often seems preferable to no certainty at all. But the answers that the natural sciences give are trustworthy not because they are final, not at all. These answers are trustworthy because they are the best we have right now, at this specific moment in the history of knowledge. The absence of certainty is by no means a weakness of science. On the contrary, it constitutes and has always constituted the very strength of rational thinking, driven by insatiable curiosity, a spirit of rebellion, and an unstoppable desire for change. It's precisely because science doesn't see its answers as final, etched in granite truths, that it can continue to improve them, deepen them, refine them. From this perspective, the 3 centuries of Newtonian science's dominance, that wasn't the whole of science. That was just a brief moment of rest in the shadow of a great success. By challenging Newton's theories, Einstein wasn't questioning the very possibility of gaining better knowledge about how the world works. On the contrary, he was following in the footsteps of Maxwell, Newton, Copernicus, Ptolemy, Hipparchus, and of course, Anaximander. Each of them pushed scientific knowledge forward by challenging the accepted view of the world, constantly improving it, by recognizing the mistakes of their predecessors and learning to see further and further. The successes achieved by these great minds, as well as by countless other less visible scientists, have repeatedly changed not only our worldview, but even the very rules of thought that structure that worldview. I'm convinced that searching for some universal key to solve all problems, some methodological and philosophical anchor to which we could tether our entire intellectual adventure, is to betray the very nature of science, which is inherently evolutionary and critical. For quite some time now, humanity has found a path that allows us to bypass both the overconfidence of those who claim to have grasped final truths and to avoid the intellectual collapse that follows the popular modern assertion that all truths are equal, each in its own cultural context, and we can't tell true from false. That path is the path of science. So turning to the ancient origins of scientific thought, to the very first tentative steps toward a rational investigation of nature, becomes a way to shed light on some central aspects of the nature of this thinking. And I think reflecting on this is important for today's fundamental science as well. The process of scientific revolution started by Einstein is far from over. To talk about Anaximander is also to try to grasp the meaning of this ongoing revolution. My main scientific work is in this very area, specifically in quantum gravity, one of the biggest open problems at the heart of modern theoretical physics. To solve a problem like that, we'll probably need to radically change our understanding of the nature of time and space once again. And Anaximander managed to change the previous understanding of space, transforming the world from a closed box with heaven above and earth below into an open cosmos in which the earth floats freely. I believe that only by understanding how such grand transformations of the world, like Anaximander's, are possible, and in what sense they are correct, can we hope to face the challenges related to, for example, the changes in our concepts of space and time required to quantize gravity. Finally, a third and equally important thread runs through this whole story. A discussion of a vast problem for which I can probably pose more questions than I can offer answers. When we look at the earliest ancient expressions of rational thinking about nature, it naturally leads us to consider the mode of knowing that historically preceded it, A mode of knowing that, even today, it asserts itself as an alternative to rational thought. It's the way of knowing from which rational thought was born, from which it separated, against which it rebelled, and against which it continues to rebel. When Anaximander, in Pliny's words, threw open the gates of nature, he inadvertently sparked a conflict between two fundamentally different ways of thinking. On one side, you had the dominant mythical and religious way of thinking, based largely on certainties that by their very nature could not be questioned. On the other, a new view of the world was emerging, based on curiosity, a desire for change, and a rejection of those very certainties. This conflict runs like a red thread through the entire history of Western civilization, century after century, and is resolved differently each time. It continues to this day. After a period when these opposing types of thought seem to have found a way to coexist peacefully, the clash between them has now erupted with new force. Numerous voices, representing political and cultural viewpoints that are otherwise strongly divergent, are once again defending irrationality and the primacy of religious thought. This new clash between positivist and mythological religious thought takes us back to the conflicts of the Enlightenment era. But I think it would be a mistake to look only at the last decade or the last few centuries to try to clarify this point. The clash we're talking about is even more fundamental. Its history is measured in millennia, not centuries, for reasons tied to the slow, almost geological development of human civilization, the deep structure of its conceptual organization, and its characteristically measured political and social evolution. These are vast, almost boundless topics, and I can only ask questions and look for grounds for reflection in the final chapters, but I believe these themes are of the utmost importance for our world and its future. Every day, the uncertain outcomes of this millennial conflict shape the lives and destinies of all humanity. I don't want to overstate the importance of Anaximander as an individual. After all, we know tragically little about him. But 26 centuries ago, on the Ionian coast, someone, perhaps it was him, opened a new path to knowledge and forged a completely new route for humanity. A thick fog of time shrouds the 6th century BC, and we know far too little about the man named Anaximander to credit him with this colossal revolution with absolute certainty. And yet this revolution, this birth of a way of thinking based on curiosity and an unquenchable thirst for change, did happen. In the end, it doesn't really matter whether these changes were made personally by Anaximander, or if Anaximander is just the name used in ancient sources to refer to them. This extraordinary revolution, which began on the coast of modern-day Turkey 26 centuries ago, and in which we are still immersed, is the main theme of our story. The 6th century BC. It's not exactly the most famous period in history. When Anaximander was born in Miletus in 610 BC, the golden age of Greek civilization, the era of Pericles and Plato, was still almost 2 centuries away. In Rome, according to legend, Tarquinius Priscus was king. Around the same time, the Celts founded Milan, and ancient Greek settlers from Ionia, Anaximander's homeland, established Marseille. Homer, or whoever was behind that name, had given the world the Iliad 2 centuries earlier, and Hesiod had written Works and Days, but none of the other famous ancient Greek philosophers, poets, or playwrights had yet begun their work. Sappho, still a very young woman, was living on the island of Lesbos, not far from Miletus. In Athens, whose power was just beginning to sprout, the strict laws of Draco were in effect. But Solon, who would go on to write the first constitution with democratic elements, had already been born. The Mediterranean world was far from primitive. People had been living in cities for at least 10,000 years, and the Old Kingdom in Egypt had existed by then for about 26 centuries, the same amount of time that separates Anaximander from you and me. 2 years before Anaximander's birth, Nineveh, the capital of the mighty and cruel Assyria, fell, marking the end of its dominion. Babylon, with a population of over 200,000, had once again become the largest city in the world, as it had been for millennia. Nabopolassar ruled Babylon, but the city's resurgence was short-lived. In the east, the power of Persia was already rising under Cyrus I, and soon the Persian Empire would establish control over all of Mesopotamia. In Egypt, it was the final year of the long reign of the great Psamtik I, the first pharaoh of the 26th dynasty. He had won Egypt's independence from the fading Assyrian Empire and restored prosperity to his kingdom. Psamtik I established close relations with the Greek world. He recruited many Greek mercenaries into his army and encouraged Greeks to settle in Egypt. In turn, Miletus maintained a thriving trading port in Egypt, now Crates. Given all this, it's safe to assume that Anaximander had direct access to extensive knowledge of Egyptian culture. A map of that time, if one existed in our modern sense, would show a boiling cauldron of empires in the Near East. Josiah of the house of David was ruling Jerusalem. As the Assyrian Empire weakened and Babylonia had yet to regain full power, he took advantage of this instability to assert Jerusalem's status and commanded his subjects to worship one God, Yahweh. He ruthlessly destroyed all ritual objects of other gods, like Baal and Astarte, demolished their temples, dealt with their living priests, and exhumed and burned the bones of their dead priests on their altars. In doing so, he established a model of behavior toward other religions that would later become characteristic of triumphant monotheism. Just before Anaximander's death, the Israelites were once again taken captive and exiled to Babylon, where they again knew slavery, a slavery from which they would eventually gain freedom, just as they had many centuries before when they left Egypt thanks to Moses. The echoes of these dramatic events undoubtedly reached Miletus, unlike, probably, much of the news from more distant parts of the world. Northern Europe was slowly transitioning from the Bronze Age to the Iron Age. On the American continent, the ancient Olmec civilization was already in decline. In northwestern India, the Mahajanapada kingdoms had formed. Mahavira, a contemporary of Anaximander, founded Jainism in India and preached nonviolence towards all living beings. You could say that the Indo-Europeans of the West were already focused on the question of how best to think about the world, while the people of the East were pondering how best to live. In China, Jan of the Zhou dynasty had recently ascended the throne, becoming the 12th emperor of the illustrious dynasty. This was the so-called Spring and Autumn period, a time of, on the one hand, decentralized power and fierce feudal battles, and on the other, incredible cultural diversity and creativity. China wouldn't know such a culturally fertile era for a long time to come. Perhaps this was the price paid for an internal stability that, while imperfect, was still far superior to the stability of the ferocious, ever-warring West. So when Anaximander was born at the dawn of the 6th century BC, human civilization had existed and been highly organized for millennia. The movement of goods and ideas between continents was intense. In Miletus, it might have already been possible to buy Chinese silk, just as it became possible 2 centuries later in Athens. Most people survived by farming, raising animals, fishing, hunting, or trading. Others, just like today, accumulated power and wealth by fighting each other. So what was the state of knowledge and the cultural climate in Anaximander's world? It's hard to say for sure, because the 6th century, unlike the more talkative eras that followed, left behind relatively few written documents. However, some great works whose influence persists to this day had already been created. The main parts of the Bible, including Deuteronomy, probably date to around this time. The ancient Egyptian Book of the Dead, the great epics like the Epic of Gilgamesh, the Mahabharata, the Iliad, and the Odyssey. Magnificent, grandiose stories in which humanity reflected on itself, its dreams and its follies. In writing had emerged 3,000 years earlier. Written laws had existed for at least 1,200 years, ever since Hammurabi, the sixth king of Babylon, inscribed his laws on magnificent basalt stelae that were erected in every city of his vast empire. One of these stelae is now on display in the Louvre, and it's hard to remain indifferent looking at it and reading the translation of its text, feeling the breath of such a distant era. And what about scientific knowledge? In Egypt, and especially in Babylon, the basic principles of mathematics had been developed, which we know about thanks to collections of mathematical problems and answers found during excavations. Young Egyptian scribes learned to perform simple division so that sacks of grain could be distributed equally among lenders or according to specific proportions. Imagine the task. A merchant has 20 sacks of grain to pay 2 workers, one of whom worked 3 times as much as the other. How many sacks should he give to each? Methods of calculation were known for dividing numbers by 2, 3, 4, and 5, but not by 7. A problem requiring division by 7 had to be cleverly rephrased in other terms. The constant we know as pi was used, just as it is today, to calculate the circumference of a circle from its diameter, but its exact value was, of course, unknown. The Egyptians knew that a triangle with sides in the proportion 3, 4, 5 has a right angle, the basis for the future Pythagorean theorem. The mathematical knowledge of the Egyptians and Babylonians was roughly equivalent to that of an advanced second or third grade student in a modern school. You often hear about the extraordinary level of development of ancient Babylonian mathematics. This statement is true, but it needs to be interpreted correctly. The Babylonians developed concepts that are now studied by 7-year-olds. But the thing is, for humanity to accumulate the knowledge that today's children receive in elementary school was extremely, unbelievably difficult. In Egypt, Babylon, or Jerusalem, in Crete or Mycenae, in China or Mexico, knowledge was concentrated in the royal and imperial courts. The fundamental form of political organization for humanity in the first great civilizations was the monarchy, a centralized system of power. You could say that the great monarchies were the great civilizations. Laws, trade, writing, knowledge, education, religion, political structure, all of this existed and developed mainly in the royal and imperial palaces. The structure of the monarchy allowed civilization to develop by guaranteeing a certain degree of security and stability. Sometimes stability was maintained, but sometimes it collapsed, just as it does today. The Babylonian court meticulously kept records of important and noteworthy facts. These included grain prices, descriptions of catastrophic events, and, what was extremely important for the future development of science, records of astronomical data such as eclipses and the positions of the planets. 8 centuries later, during the Roman Empire, the great astronomer Ptolemy was still using data from the ancient Babylonian archives and considered them reliable enough. He lamented the lack of access to the complete collection of Babylonian documents on the positions of the planets, but he had at his disposal tables of eclipses compiled during the reign of Nabonassar around 747 BC, that is, a century before Anaximander. Ptolemy even chose the beginning of Nabonassar's reign as year 0 for his meticulous astronomical calculations. And we can find records of astronomical data even further back in antiquity. In particular, one cuneiform tablet, now in the British Museum and inscribed in Nineveh in the 7th century BC, contains the correct positions of Venus in the sky for many years during the reign of Ammisaduqa around 1600 BC, a whole millennium before Anaximander. It's worth pausing for a moment to reflect on this ancient astronomy because it has a direct bearing on the future of science. What did this data mean to the Babylonians? Why did they record it so diligently? Why did the Babylonians watch the heavens at all? The reason for their interest in the heavens is clearly stated on hundreds of thousands of surviving ancient tablets. On the one hand, people noticed the regularities of certain astronomical phenomena and derived purely practical benefits from them, for example, for agriculture. On the other hand, they were desperately trying to establish a connection between astronomical and earthly phenomena. The Mediterranean climate requires farmers to carefully follow annual cycles. But how is it possible to keep such a precise rhythm in a world without calendars and newspapers, and in a region where the seasons, at first glance, are practically indistinguishable? The sky and the stars offered a relatively simple solution. People had known this for centuries, and this knowledge was widespread. For example, Hesiod in Works and Days describes it in beautiful, almost hypnotic language. When Arcturus rises from the sacred streams of ocean and shines all night long at dusk, after him, with the coming of spring, the swallow, Pandion's daughter, appears to men with her shrill, loud song. It is best to prune the vines before she appears. And further, when Sirius and Orion are high in the middle of the sky, and rosy-fingered dawn begins to see Arcturus, cut, Perseus, and bring home the grape clusters. After the Pleiades, the Hyades, and the might of Orion set in the west, remember that the time for sowing has come. This is how you should divide the fieldwork throughout the year. Hesiod and other authors believed in the clever scheme of the heavens and human life, but they were not acting as scientists. That is, they were meaningful, but they had no desire to investigate the methodology behind these views. They accepted that this phenomenon existed, and that predetermined relations governed the functioning of the world, but did not require any explanation. The Perses, to whom Hesiod refers in the poem, was his brother. And here's another piece of advice for the sailor. But if you wish to sail the dangerous sea, remember, after the terrible might of Orion drives the Pleiades from the sky and they fall into the misty, foggy sea, various winds begin to blow with furious force. In short, according to Hesiod, the month of the year is easily determined by observing the stars. When Arcturus appears over the sea at dusk, spring arrives. Autumn begins when the constellation Orion and Sirius, the dog star, are directly overhead. And autumn ends and winter begins when the Pleiades have completely set below the horizon. Also, according to the Bible, Yahweh created the stars on the fourth day to serve as signs to mark sacred times and to mark days and years. So it's clear that for centuries, farmers understood far more about the movement of the sun and stars across the sky than the average educated person does today. Hesiod speaks as if it's common knowledge that to determine the time of year, you just have to look at the constellation visible in the east at dawn. Few modern university professors possess such a seemingly simple skill. At times, Hesiod seems to be talking about the stars themselves as the causes of human behavior, as in his extraordinary verses about the summer heat. In the season when the artichokes bloom and the cicada sitting on a tree pours out its shrill song from under its crackling wings in the sweltering summer heat, goats are fattest and wine is best, women are most lustful, and men are weakest. Sirius parches their knees and heads mercilessly. It's hard to say whether this should be understood as Sirius causing male weakness, or if the dog star here simply denotes summer itself. In this context, such a distinction might be irrelevant. Perhaps Hesiod simply means that when Sirius is high in the sky, in summer, people are weak, and there's no talk of cause and effect here. We ourselves sometimes say, "Noon makes me sleepy," without thinking about whether the fatigue is caused by the time of day or by lunch. This brings us to the second and more important role of ancient astronomy, as an attempt to establish a connection between celestial phenomena and events of direct importance to humans. The question of the dependence of world events on celestial events has concerned people since the earliest antiquity, and it doesn't matter whether this dependence was understood as causal or as a simple coincidence. In fact, it's unknown whether such a distinction even mattered in the 6th century BC. Let's go back to Babylonia. On that very tablet with the observations of Venus, for example, we find, "On the 15th day of the month, Venus disappeared. It was gone from the heavens for 3 days. Then, on the 18th day of the 11th month, it reappeared in the east. New springs flowed. The god Adad sent rain. The goddess Ea sent her floods." This kind of notion, linking events in the heavens and on earth, is found almost everywhere in the ancient cuneiform texts about astronomy that have come down to us. Here is another example from the same period, explaining the appearance of the sun in the sky before dawn. If in the month of Nisanu, the first month of the Babylonian calendar, the sun at dawn appears spattered with blood and the light is cold, then rebellion on earth will not cease, and the god Adad will perform a slaughter. If on the first day of the month of Nisanu, the dawn appears spattered with blood and the light is cold, then the king will die, and there will be mourning on the land. All Babylonian documents clearly show that the collection of astronomical data, for example about eclipses and the position of the planets, was motivated by a deep belief that this information was related to events of direct interest to humans: wars, floods, the deaths of rulers, and so on. This belief, of course, seems completely wrong to us today. But to this day, it is professed by perhaps the majority of people, even in highly educated countries, and even by those who hold very high positions. The Babylonians collected astronomical data and looked for patterns and connections between events in the heavens and on earth. But the relationship between the celestial events themselves was also of interest to them. We cannot rule out that someone in Anaximander's time was able to predict eclipses with a certain accuracy, or, in the case of solar eclipses, to predict at least the date when such an eclipse might occur. This is not so difficult, as there are certain patterns in the time intervals between eclipses. A smart and interested person, having studied the accumulated data, could quite easily find these patterns. The ancient Greeks reported with amazement that Thales, Anaximander's supposed teacher, predicted a solar eclipse, although no one knows for sure how he managed it. We don't know if this story is true, but it's very likely that Thales visited the Babylonian court and could have familiarized himself with their astronomical tables. Events on the other side of the planet illustrate another, no less important purpose of astronomy. In the 6th century BC in China, the famous Imperial Institute of Astronomy had probably already been founded. According to the Shu Jing, Book of Documents, which dates to around 400 BC, the study of astronomy in China began under the legendary Emperor Yao, who lived approximately 2,000 years before our era. The Shu Jing says that Yao commanded the brothers Shi and He, in reverent accordance with the wide heavens, to create a calendar based on the movements of the sun, the moon, the stars, and the constellations, and respectfully to deliver the knowledge of the seasons to the people. She and he each had 2 sons, who were sent to the 4 corners of the earth with the task of determining when the solstices and equinoxes occurred there. The main question that prompted the investigation of astronomical phenomena and the founding of the Institute was undoubtedly the problem of the calendar. The development of real astronomical knowledge in China most likely belongs to the period of the Han Dynasty, meaning it began about 2 centuries after Anaximander and much later than in Babylonia. Over the following millennia, Chinese astronomers developed rudimentary techniques for predicting the positions of planets and eclipses. However, the successes of the Imperial Institute of Astronomy in China were far from brilliant, despite the fact that, first, it existed almost without interruption for more than 20 centuries, and second, it had at its disposal astronomical observations collected over thousands of years, as well as some of the most brilliant minds of the empire. And even 300 years ago, the Institute's methods for predicting celestial phenomena were significantly inferior to the methods described by Ptolemy in the Almagest more than 15 centuries earlier. Moreover, the Institute had not yet realized the fact that the Earth is round. The interest of the Chinese imperial authorities in astronomy was driven not only by the need to create a calendar, but also by deep religious and ideological considerations. The official cult of Confucius, like the religions of ancient Greece and modern Europe, taught that heaven is the dwelling place of the divine. The emperor was the mediator between heaven and earth, the one who guarantees and maintains order, simultaneously worldly, social, and cosmic. The Imperial Institute of Astronomy had the crucial mission of establishing the official schedule of rites to establish harmony with the august heaven. The history of astronomy in China clearly shows that it is not enough to simply observe celestial phenomena for many centuries, even with the full support of political authorities, to arrive at science in its modern sense, like that of Copernicus, Kepler, Galileo, and Newton. Moreover, it was not even enough to develop an effective, predictive, and accurate mathematical theory like that of Hipparchus and Ptolemy. And it certainly wasn't enough for a clear progress in understanding the structure of the world, as happened with Anaximander. Similarly, the ancient Mesopotamian civilizations observed celestial phenomena continuously and persistently for millennia, but they never progressed beyond collecting rather inaccurate data, which were interpreted within a completely erroneous conceptual framework that linked these phenomena to earthly events. The motives and character of the study of the heavens by astronomers in China and Babylonia were not necessarily the same, but they were united by the fact that they showed the possibility of studying astronomy in the context of a worldview completely alien in form and motivation to the worldview of Anaximander, Ptolemy, Copernicus, and Einstein. The central question of our narrative is precisely what caused the motives and logic of ancient Near Eastern and ancient Chinese astronomy to differ so strikingly from the motives and logic of these giants of thought. But let's return to the region that interests us most here, the Greek world, where Anaximander was destined to be born. Hesiod, who was writing a century before our hero's birth and was undoubtedly well known in Miletus, gives us a general idea of the culture of ancient Greece before Anaximander. The world, according to Hesiod, comes from man. It's built on hard peasant labor and positive, healthy moral values. Hesiod asks questions about the meaning of human life and labor in Works and Days, and about the birth and history of the universe in the Theogony, anticipating themes and ideas that would become the driving force of the great philosophical quests in the centuries to follow. Hesiod's answers to these questions are, of course, complex, but they are clearly made of the same stuff we find all over the world, particularly in the Tigris and Euphrates Valley, the stuff of gods and myths. Let's consider one example. How did the world come into being? What is it made of? Hesiod gives the answer at the very beginning of the Theogony. First of all, chaos came to be, but then Gaia, the broad-bosomed, the ever-sure foundation of all, and dim Tartarus in the depth of the wide-pathed earth, and Eros, fairest among the deathless gods. But Gaia's firstborn was one who was her equal in every dimension, starry Uranos, heaven, so that he should cover her all over. And then, bedded with Uranus, she bore the deep-swirling Oceanus. After them was born the youngest of all, crooked counseling Kronos, who was the most terrible of her children, and he hated his mighty father. And so on in that same magnificent epic style. Similar descriptions of the origin and structure of the world are found in the mythology of almost all civilizations. Remember the Babylonian creation myth Enuma Elish, which was recited on the 4th day of the new year. Its text was discovered on cuneiform tablets from the 12th century BC, 500 years before Hesiod. When the heavens above did not exist, and the earth beneath had not been named, Apsu the firstborn their begetter, and creator Tiamat, who bore them all, mingled their waters together, when no gods whatever had been brought into being. Then were the gods created in their midst. The resonance with Hesiod's text is striking. All the evidence that has come down to us indicates that it was through these myths that humanity tried to order the world. People interpreted earthly events as being shaped by the forces of gods and supernatural beings. Almost all ancient texts in one way or another tell of gods. Gods give the world structure, act as characters in all the great tales, serve as justification for the power of monarchies, are identified with that power, are referred to in the judgments of individuals and groups, and finally, gods are the guarantors of law. All ancient civilizations are united by the idea of the centrality of the divine. Gods played a fundamental role in the development and order of civilization, at least from the times for which we have written records. Why did all of humanity create and accept a system of thought in which gods play such an all-encompassing role? When and why did this essentially strange structure of thought arise? These are key questions for understanding the nature of civilization, and the answers are still far from being found. But the central position and universality of polytheistic gods as a basic element in the structure of ancient thought is beyond any doubt. When Anaximander was born, the foundation for knowledge was sought exclusively in myth and the divine. A completely different atmosphere, strikingly different from the one that reigned in Jerusalem, Babylonia, or Egypt, pervaded the young, rapidly developing cities of the emerging Greek civilization, which were in a state of powerful geographical, economic, commercial, and political expansion. In all forms of expression of this young culture, something new, something fresh was already breaking through. For example, in Ionian sculpture, which anticipated the naturalism and many forms of classical Greek art. One only has to look at the Kroisos Koros, a life-sized marble statue sculpted probably during Anaximander's lifetime, to feel this new energy, this striving for realism, for the human. The novelty of this culture shone even brighter in the earliest lyric poetry, strikingly different from anything written before. The words of Sappho, flowing like honey, full of passion and tenderness, paint a completely different inner world. He seems to me equal to the gods, that man who sits across from you and listens close to your sweet speaking and your lovely laughter. My tongue is broken, and a thin fire runs under my skin. I am drenched in sweat. A trembling takes me all over. I am greener than grass, and I seem to be little short of dying. This was something absolutely new, the voice of individual feeling, expressed with such force and frankness. But it was the new complexity of the political structure that especially reflected the radical novelty of the Greek world. While the peoples of the entire planet were trying to achieve stability and striving to create great kingdoms and empires, modeling themselves on the millennial rule of the pharaohs, Greece remained divided into many independent city-states, the polis, each jealously guarding their autonomy. This seemingly fragmented structure turned out to be anything but a source of weakness. It was the basis of an extraordinary dynamism that led the Greek world to enormous success, both political and cultural. Anaximander's intellect did not flourish in the rich and efficient bureaucracy among the pharaoh's scribes, nor at the highly organized court of ancient Babylonia, where the knowledge of the ancient world was kept. No, it flourished in a young, independent, prosperous Ionian city on the seacoast, Miletus. Merchant ships came and went continuously, and the inhabitants of Miletus probably considered themselves masters of their personal and civic destiny to a much greater extent than any subject of a pharaoh or Babylonian king. Ionia was a small region on the coast of Asia Minor, comprising a dozen cities facing the sea and protected by a steep, rugged coastline. Here, on this small, almost unknown strip of land, the earliest example of critical thinking was born, that very free spirit of inquiry that would later define all of ancient Greek and, ultimately, modern thought. Human civilization owes an enormous, unpayable debt to this land, perhaps even greater than to Egypt, Babylonia, or even Athens. Also on the Ionian coast, but closer to the center of Asia Minor, was the rich Lydian kingdom, which a few decades earlier had minted the world's first coins. Elaeus II, king of Lydia, took the throne in 610 BC, the year of Anaximander's birth, and continued to wage war against Miletus, a war started by his father. However, Elaeus was soon forced to turn his attention to military actions against Babylonia and the Median kingdom, which were advancing from the southeast. He made peace with Miletus and left the city untouched. Elaeus's tomb, a huge earthen mound, still stands on the plain between Lake Marmara and the Gades River, north of Sardis in modern-day Turkey. The cities of Ionia were inhabited by Greeks. They probably arrived from different parts of Greece long before, perhaps a century or two after the Trojan War, and mixed with the local population. The cities of Ionia were independent but united in the Ionian League, a confederation that was essentially mostly cultural and religious. Being something of a Greek outpost in the ancient civilizations to the south, Ionia was famous for its wealth and fertility. Ionia's wealth was ensured not only by highly valued local products, such as olive oil from the groves that still surround the ruins of Miletus today, but also by lively trade with the peoples of the north who lived by the Black Sea. Ionia controlled an important transit route, which had enriched Troy many centuries before. Trade with Asia was also of great importance. Goods traveled along caravan routes through Asia Minor and arrived at the markets of Syria. Ships of the Phoenicians, from whom the Greeks, by the way, got their alphabet, arrived from the south. Ionia was a true crossroads, a connecting link between the west and east. The Greek cities had a significant number of slaves, a mixed economy, agriculture, craftsmanship, and trade, and free citizens who took up arms when necessary. In the 6th century BC, Miletus was the most prosperous city in Ionia, and possibly in the entire Greek world. The rise of Athens and Sparta came later. It was also the city most closely located to the great civilizations to the south. The historian Herodotus, for good reason, called Miletus the Pearl of Ionia. The novelty of this culture shone even brighter in the earliest lyric poetry, strikingly different from anything written before. The words of Sappho, flowing like honey, full of passion and tenderness, paint a completely different inner world. He seems to me equal to the gods, that man who sits across from you and listens close to your sweet speaking and your lovely laughter. My tongue is broken, and a thin fire runs under my skin. I am drenched in sweat. A trembling takes me all over. I am greener than grass, and I seem to be little short of dying. This was something absolutely new, the voice of individual feeling, expressed with such force and frankness. But it was the new complexity of the political structure that especially reflected the radical novelty of the Greek world. While the peoples of the entire planet were trying to achieve stability and striving to create great kingdoms and empires, modeling themselves on the millennial rule of the pharaohs, Greece remained divided into many independent city-states, the polis, each jealously guarding their autonomy. This seemingly fragmented structure turned out to be anything but a source of weakness. It was the basis of an extraordinary dynamism that led the Greek world to enormous success, both political and cultural. Anaximander's intellect did not flourish in the rich and efficient bureaucracy among the pharaoh's scribes, nor at the highly organized court of ancient Babylonia, where the knowledge of the ancient world was kept. No, it flourished in a young, independent, prosperous Ionian city on the seacoast, Miletus. Merchant ships came and went continuously, and the inhabitants of Miletus probably considered themselves masters of their personal and civic destiny to a much greater extent than any subject of a pharaoh or Babylonian king. Ionia was a small region on the coast of Asia Minor, comprising a dozen cities facing the sea and protected by a steep, rugged coastline. Here, on this small, almost unknown strip of land, the earliest example of critical thinking was born, that very free spirit of inquiry that would later define all of ancient Greek and, ultimately, modern thought. Human civilization owes an enormous, unpayable debt to this land, perhaps even greater than to Egypt, Babylonia, or even Athens. Also on the Ionian coast, but closer to the center of Asia Minor, was the rich Lydian kingdom, which a few decades earlier had minted the world's first coins. Elaeus II, king of Lydia, took the throne in 610 BC, the year of Anaximander's birth, and continued to wage war against Miletus, a war started by his father. However, Elaeus was soon forced to turn his attention to military actions against Babylonia and the Median kingdom, which were advancing from the southeast. He made peace with Miletus and left the city untouched. Elaeus's tomb, a huge earthen mound, still stands on the plain between Lake Marmara and the Gades River, north of Sardis in modern-day Turkey. The cities of Ionia were inhabited by Greeks. They probably arrived from different parts of Greece long before, perhaps a century or two after the Trojan War, and mixed with the local population. The cities of Ionia were independent but united in the Ionian League, a confederation that was essentially mostly cultural and religious. Being something of a Greek outpost in the ancient civilizations to the south, Ionia was famous for its wealth and fertility. Ionia's wealth was ensured not only by highly valued local products, such as olive oil from the groves that still surround the ruins of Miletus today, but also by lively trade with the peoples of the north who lived by the Black Sea. Ionia controlled an important transit route, which had enriched Troy many centuries before. Trade with Asia was also of great importance. Goods traveled along caravan routes through Asia Minor and arrived at the markets of Syria. Ships of the Phoenicians, from whom the Greeks, by the way, got their alphabet, arrived from the south. Ionia was a true crossroads, a connecting link between the west and east. The Greek cities had a significant number of slaves, a mixed economy, agriculture, craftsmanship, and trade, and free citizens who took up arms when necessary. In the 6th century BC, Miletus was the most prosperous city in Ionia, and possibly in the entire Greek world. The rise of Athens and Sparta came later. It was also the city most closely located to the great civilizations to the south. The historian Herodotus, for good reason, called Miletus the Pearl of Ionia. However, Miletus existed long before it was colonized by the Greeks. It is mentioned as Miliwanda in Hittite annals of the 14th century BC. Herodotus writes that Neleus, the youngest son of Codrus, king of Athens, founded the Greek Miletus around 1050 BC. But the monarchy in Miletus died out by the end of the 8th century, giving way to complex political processes. Miletus went through a period reminiscent of events in Athens and the later historical saga in Rome. A king, exiled by the aristocracy, which in turn finds itself threatened by a wealthy merchant class. There were long political battles here, centered on the conflict between the Plutus, the rich, and the Hieromacha, the laborers. This political complexity, this internal struggle and search for new forms of government, was the feature that most distinguished Greek culture from the monarchical kingdoms of the East, and it was this that formed the basis of the emerging cultural revolution. In 630 BC, 20 years before Anaximander's birth, the dictator Thrasybulus came to power, who probably received the support of the people who wanted to overthrow the aristocracy. Thrasybulus led Miletus to the peak of its power. In the early 6th century, when Anaximander was born, Miletus was a thriving city, one of the most important trading ports of the Greek world, with about 100,000 inhabitants. It controlled a small but influential maritime empire with dozens of colonies scattered along the coast of the Black Sea and even in Italy and modern France. The city traded in grain, timber, fish, metals, wool, linen, spices, papyrus, ivory, and perfumes. Miletus itself produced and exported terracotta, weapons, oil, furniture, textiles, and wine. The Miletian authorities founded the trading port of Naucratis in Egypt around 620 BC. Miletus certainly had no shortage of trade and cultural contacts with the ancient civilization of Egypt. A strong Egyptian influence is also noticeable in architecture. The first monumental Greek temples of that period were inspired by Egyptian models. Colonies and trade brought not only wealth, but also the priceless opportunity for interaction with different peoples, ideas, and opinions. As the economy grew, so did the world view of the Milesians. So, Miletus was a rich, free city, capable of independently resisting the ambitions of Lydia, and probably the Greek city most exposed to the influence of the advanced cultures of the south. Unlike the great cities of Mesopotamia and Egypt, Miletus had neither a huge royal palace nor a powerful caste of priests. This city of free citizens was located at the very heart of cosmopolitanism, a city that was prosperous and in a phase of extraordinary flourishing of art, politics, and culture. Miletus was the heart of the first thriving humanism. The picturesque ruins of Miletus that we see today do not belong to the time of Anaximander. In 548 BC, a year before his death, Anaximander probably saw his city conquered by the Persian Empire. And a few decades later, in 490 BC, after a failed revolt, Miletus was sacked and destroyed by the Persians. This episode marked the end of Miletus's cultural primacy. Anaximander, it seems, was an important figure in Miletus. According to one source, Claudius Aelianus, he even led the Milesian colony in Amphipolis. Thales, one of the 7 legendary sages of ancient Greece, lived in Miletus shortly before Anaximander. Thales traveled a lot and was actively involved in public life. They undoubtedly knew each other. Ancient sources testify to Anaximander's journey to Sparta, where he reportedly built a sundial. And according to Cicero, Anaximander even saved the lives of many Spartans by predicting an earthquake. This story seems unlikely, but it paints a picture of Anaximander as a traveler, a respected and well-known man. Some authors also believe he may have traveled to Egypt via Naucratis. No portraits or detailed descriptions of Anaximander have survived. Diogenes Laertius mentions that the philosopher Empedocles, in an attempt to imitate Anaximander, put on a solemn air and a theatrical manner, perhaps a faint hint of Anaximander's own mannerisms. Since he recorded his thoughts, he must have had access to other written texts as well. However, we know almost nothing about what he read, his personal life, his character, his appearance, or the details of his travels. But for us, the primary interest lies in his ideas, his revolutionary vision of the world. Anaximander wrote a treatise in prose titled On Nature. Alas, this work is lost. Only a single but precious fragment has survived, quoted by Simplicius of Cilicia in his commentary on Aristotle's Physics. These words, translated from Greek, sound something like this: "All things arise from one another and disappear into one another, according to necessity. They render justice and pay penalty to one another for their injustice, according to the assessment of time." Much has been written about this handful of mysterious words. It's always hard to be sure when it comes to interpreting a passage torn from its original context. This is the only direct witness to Anaximander's work, yet it tells us little about what in his ideas is truly of revolutionary interest. Fortunately, many Greek sources convey the content of Anaximander's book, although most of them are from a later time. All are indirect and sometimes not very reliable. Among the most interesting is Aristotle himself, who wrote just 2 centuries after Anaximander and repeatedly discussed his ideas. It's very likely that Aristotle had a copy of Anaximander's text in his famous library. Theophrastus, a student of Aristotle, described Anaximander's ideas in detail in his work on the history of philosophy. This work by Theophrastus is also lost, but a number of later authors, such as Simplicius, who lived in the 6th century AD, contain extensive information from it. Today, trying to reconstruct Anaximander's ideas from these numerous, varied, and late sources becomes a most complex intellectual puzzle. Of course, the charred scrolls found in the excavations of ancient Roman libraries are now being unrolled and deciphered with increasingly sophisticated techniques. The same can be said for X-rays of the wrappings of Egyptian mummies, which were often made from strips of papyrus manuscripts. So we can still hope that the text of Theophrastus, or perhaps even Anaximander himself, will one day be found. But for now, to know the content of his book, we must rely on reconstruction from indirect sources, drawing on the work of researchers like Charles Kahn, Marcel Conche, Dirk Couprie, and Daniel Graham. So what was likely in Anaximander's lost treatise on nature? First, he argued that the transformation of one thing into another is governed by a certain necessity that determines how phenomena unfold in time. Second, the multitude of things that make up nature comes from a single origin or principle called the apeiron, something indefinite or infinite. Third, the world came into being when the hot and the cold separated from this apeiron. This separation gave rise to the cosmic order. A ball of fire enveloped the air and the earth like the bark of a tree. Then this ball broke apart and was enclosed within wheels that formed the sun, the moon, and the stars. Originally, the earth was covered with water, which gradually evaporated. Fourth, and this is perhaps the most revolutionary, the earth is a body of finite size floating in space. It doesn't fall because there is no particular direction in which it could fall. It is not dominated by any other body. Fifth, the sun, moon, and stars revolve around the earth in complete circles. Huge wheels, like the wheels of a chariot, carry them along these circles. Inside, these wheels are hollow, like a bicycle tire, filled with fire, and have openings through which we see this fire as the sun, moon, and stars. The stars, in his view, are on the wheel closest to us, the moon on the middle one, and the sun on the farthest, and they are distant from the Earth in proportions of 9, 18, and 27 arbitrary units. Sixth, meteorological phenomena are caused by natural causes. Rainwater is water from the sea and rivers that evaporates under the heat of the sun, is carried by the wind, and then falls to the earth. Thunder and lightning arise as a result of collision and separation of clouds. Earthquakes occur as a result of fissures forming in the earth, caused, for example, by excessive heat or precipitation. Seventh, all animals came from the sea, or from the primordial moisture that once covered the earth. Thus, the first animals were either fish or fish-like creatures. When the water evaporated from some areas, they moved to land and adapted to life there. In particular, man could not have born in his present form because infants are not capable of independent existence. Therefore, the first humans must have grown from some fish-like creatures that could nurse them. To these theories, we can add a few more important points. Anaximander drew the first known map of the world. He wrote the first prose text on natural phenomena, breaking with the tradition of presenting such ideas in verse, as Hesiod did. He is traditionally credited with introducing the gnomon, a vertical rod for measuring shadows, to the Greek world, possibly having seen it in Babylonia. And some authors report that Anaximander was the first to measure the inclination of the ecliptic, the apparent path of the sun across the sky. Even if this list is not complete, even if some details can be disputed, the sum of these ideas paints a portrait of a thinker of truly colossal scale. Before we dive into Anaximander's cosmology and the mysterious apeiron, it's crucial to dwell on an aspect of his ideas that is often considered secondary, but which in fact is of central importance. I'm talking about his understanding of atmospheric phenomena in purely naturalistic terms. We know, for example, from Hippolytus, that Anaximander believed that rain comes from the vapors that rise from the earth under the influence of the sun. From Aetius and Simica, we learn that thunder, flashes, lightning strikes, hurricanes, and typhoons, according to Anaximander, all these phenomena come from the wind. And what is wind? Again, we turn to Aetius. According to Anaximander, wind is a flow of air in which the finest and moistest particles are set in motion and mixed by the influence of the sun. Ammianus Marcellinus informs us how Anaximander explained earthquakes. Anaximander says that drying out, from excessive dryness of heat or from moisture after downpours, the earth opens up huge cracks into which the outside air penetrates, and, shaken, it trembles on its foundations. If you read these ideas in the general context of Greek culture, they might just seem to confirm the Greeks' interest in the weather. If you look at them from the heights of modern knowledge, they seem like naive attempts, sometimes correct. Rain really does come from evaporation, sometimes wrong. The causes of earthquakes are more complex. Both of these readings miss something fundamental. In all the texts written before Anaximander, natural phenomena like rain, thunder, earthquakes, and wind were always explained exclusively in mythical and religious terms, as manifestations of the inscrutable will of the gods. Zeus threw lightning bolts and sent rain. Aeolus controlled the winds. Poseidon shook the earth and raised the sea waves. Before the 6th century BC, we find no trace of anyone trying to understand these phenomena as the result of natural causes, independent of the whims of deities. At some point in human history, the idea arose that one could understand these phenomena, their interconnections, causes, mechanisms, without reference to the gods. This grand turning point occurred in Greek thought in the 6th century, and all ancient texts invariably associate it with Anaximander. This transition is often overlooked. Ancient authors recognized the novelty of Anaximander's naturalism, but his explanations had not yet achieved great success at the time. To modern people, it seems so obvious that atmospheric phenomena have natural causes, that we forget what a gigantic conceptual leap was necessary for this. In Greek religion, the sky was the abode of the gods, and meteorological phenomena were their main way of revealing themselves. To seek a naturalistic interpretation of these phenomena meant a decisive break with the religious understanding of the world. A century and a half after Anaximander's death, Aristophanes, in his comedy The Clouds, ridiculed the naturalistic explanation of thunder and lightning, which was still perceived as blasphemous toward Zeus. Strepsiades, one of the characters, asks Socrates, who in the play represents the new philosophers, "And you know, I used to think that Zeus was peeing through a celestial sieve, but now, explain to me, who makes the thunder?" Socrates replies that it's the clouds, filled with water, that collide and explode with a crack. "Who pushes them against each other, tell me? Isn't it Zeus who shakes the clouds?" Strepsiades presses. "Not at all, Zeus. It's the whirlwind," Socrates answers. "Well, I'll be. So it's the whirlwind, and I, a country bumpkin, didn't know that Zeus is already retired, and the whirlwind is in his place ruling the universe?" The comedy ends with Socrates and his friends, corrupters of youth and blasphemers, being beaten. Funnily enough, 25 years later, the real Socrates was tried by an Athenian court and sentenced to death on these very charges, for corrupting the youth and not honoring the gods. He was accused of believing that meteorological phenomena could be understood without reference to the gods. That is precisely the bold hypothesis of Anaximander. The idea that rain could be caused by the movement of the wind and the heat of the sun without the direct intervention of Zeus was probably as disconcerting to a pious Greek of that time as the idea that the human soul is simply the result of the interaction of atoms is to a modern devout believer. But with one difference. The modern believer has been fighting naturalism for 26 centuries, while Anaximander, as far as we can tell, was the first to propose such a naturalistic understanding of the world. Anaximander's naturalistic theory extends far beyond meteorology, encompassing cosmology and the origin of life. Compare Hesiod's description of the world's origin. First of all, chaos came to be, but then broad-bosomed Gaia, with Anaximander's. The world appeared when the hot and the cold separated from the aporon. A ball of fire enveloped the air and the earth, like the bark of a tree. As Daniel Graham recently pointed out, the similarity of intent is obvious. Both aim to describe the origin of the world. But their methods are radically different. Hesiod tells the story of the world as a series of deeds of the gods. Anaximander, however, radically breaks with this tradition. In his story of the world, there isn't a trace of the supernatural. He explains the things of the world in terms of worldly things themselves: fire, cold, heat, air, earth. And it is the worldly things, the sun, the stars, the earth, that require explanation. This doesn't mean Anaximander foresaw the Big Bang Theory. It means he proposed a methodology that allows for explaining the world in materialistic terms, and this methodology has proven to be incredibly effective. The Big Bang Theory, like Anaximander's theory, is an attempt to understand the history of the world exclusively in terms of natural things, without reference to the divine. Another area where Anaximander's naturalism led to incredible insights is his reflections on the origin of man and life. According to Anaximander, life began in the sea. He unequivocally spoke of the evolution of living organisms linked to changes in climatic conditions. First, marine organisms appear, which as the land surface increases, migrate to it and adapt. He even wondered from what creatures the first humans could have descended, since human infants are helpless. Scientists would not return to these questions for millennia, until Darwin. The fact that these ideas, albeit in a nascent form, already existed in the 6th century BC is truly breathtaking. Even if some of Anaximander's specific explanations were wrong, the very fact that he proposed looking for natural causes of phenomena marks the birth of the scientific investigation of the world. And, by the way, not all of his explanations were incorrect. The origin of rain is indeed related to the evaporation of water by the sun's heat. The key event in an earthquake is indeed a rupture in the earth. Life did indeed originate in the seas and evolve onto land. How did he do it? Perhaps it was a matter of simple, healthy skepticism. Hecataeus of Miletus, who based his work on Anaximander's map, began his genealogies with the words, "Hecataeus of Miletus thus speaks, I write these things as they seem to me to be true, for the tales of the Hellenes are many and ridiculous as it seems to me." Once the idea of seeking naturalistic explanations was voiced, and this skepticism was born, reasonable explanations began to follow from simple observation. Remember how in school we studied the water cycle. A drop falls as rain, flows in rivers, reaches the sea, evaporates, is carried by the wind, and falls as rain again. The first person to understand this cyclical journey of water was Anaximander of Miletus. Today, many are convinced that in medieval Europe, the Earth was considered flat, and Columbus was supposedly opposed by people who feared he would fall off the edge of the world. This legend has no basis in fact. Dante in the Divine Comedy, written 2 centuries before Columbus, clearly describes the Earth as a sphere. No educated person in medieval Europe believed in a flat Earth. St. Augustine and Thomas Aquinas unequivocally pointed to its spherical shape. The objections of the Spanish scholars to Columbus were much more well-founded. The size of the Earth had been known since the 3rd century BC, when Eratosthenes, the head of the Library of Alexandria, measured it with astonishing accuracy. The Earth was too big to circumnavigate without stops with the technology of Columbus's time. Columbus, however, tried to convince everyone that the Earth was smaller, and died believing he had reached Asia. His mistake paradoxically changed the course of history. The belief in a spherical Earth was established in Greece by the time of Aristotle, who provided convincing arguments in its favor. The generation preceding Aristotle was already familiar with this concept. In Plato's Phaedo, Socrates asserts that the Earth is a sphere, although he adds that he himself cannot prove it. This is the oldest direct evidence of a belief in the spherical shape of the Earth. Plato mentions it as if it were already a well-known idea. Where did it come from? It is sometimes attributed to Parmenides, but more often it is considered to be of Pythagorean origin. Anaximander, however, did not think of the Earth as spherical. He spoke of a cylindrical shape, resembling a flat drum or a thickened disc. Quote, "The Earth is a body suspended in the air, held up by nothing, but remaining in place on account of its equal distance from all points on the periphery of the cosmos. Its shape is curved, rounded, like a stone column drum. Of its 2 flat surfaces we walk on one, and the other is opposite it." End quote. This choice of shape might seem strange. Perhaps it's related to the teachings of Thales, who imagined the Earth as a disk floating on water. Anaximander removed the supporting ocean, leaving the disk to float. From a scientific point of view, the key step wasn't taken when it was established that the Earth was cylindrical or spherical, but when it was understood that the Earth is a finite body floating freely in space. The Earth is actually not a cylinder or a sphere, but an ellipsoid, slightly flattened at the poles, or even something like a pear. These refinements are important, but they are not a conceptual revolution. The revolution is the transition from a flat, supported Earth to a rock floating in space, surrounded by sky both above and below. This is Anaximander's main contribution. The fact that the Chinese Imperial Institute of Astronomy did not make this leap in 2,000 years proves its difficulty. The transition from a cylindrical Earth to a round one, however, was simple and happened in just one generation. The first great cosmological revolution is entirely Anaximander's achievement. But how did he manage to understand that there is sky beneath the Earth? The evidence was everywhere. The sun sets in the west and rises in the east. How does it move at night? The stars rotate around the North Star, some of them disappear below the horizon and reappear. Obviously, they pass under something. For them to be able to do this, there must be space below. If they fly under the Earth, then below it is emptiness. The structure of this discovery is similar to the discovery of the water cycle. Water disappears from the sun and appears from the sky as rain. The sun disappears in the west and appears in the east. The mind connects the disappearance with the appearance and seeks a path, an empty space under the Earth. Easy? If it were so easy, why did humanity believe otherwise for millennia? Why didn't the Chinese realize this until the 17th century? The difficulty is that the idea of a floating Earth fundamentally contradicts our direct experience. Objects fall. If nothing holds the Earth up, it must fall. Anaximander's genius is revealed in his answer to the question, why doesn't the Earth fall? Aristotle conveys it like this: the Earth doesn't fall because there are no special reasons for it to fall. For that which is situated in the center and at an equal distance from all extremes, it is no more fitting to move up than down or to the sides. But it is impossible to move in opposite directions at the same time, so it must necessarily remain at rest." End quote. Aristotle called this theory ingenious. Anaximander turned the question around. Why should the Earth fall? He questioned the extrapolation of falling from ordinary objects to the Earth itself. Heavy objects fall because they are near a huge body, the Earth, which prevails over them and determines the direction of falling towards the Earth. But the Earth itself has no such direction because nothing prevails over it. Objects don't fall in the direction of an absolute down, they fall towards the Earth. In this theory, the very meanings of the words up and down become relative. Down no longer indicates an absolute direction in the cosmos. As Hippolytus would later say, conveying Anaximander's thought, for those who stand on their feet below, at the antipode, high things are low and low things are high, and so all over the earth. End quote. This is a radical change in perspective on the cosmos, similar to the revolutions of Galileo and Einstein. Galileo showed that there is no absolute rest and motion. Einstein showed that there is no absolute simultaneity. Anaximander, based only on the observation of the stars, remade the universe, changing the very grammar of our understanding of space. He said, "The world is not as it seems. Our point of view is limited. Reason and observation allow us to understand that our prejudices are wrong. In cosmic space, there is no priority direction for falling. For the Earth itself, there is no down." This is a radical conceptual move, and it turned out to be correct. Karl Popper called this Anaximander idea one of the boldest, most revolutionary, and most portentous ideas in the whole history of human thought. End quote. Dirk Couprie also points to another innovation. Anaximander, by speaking of different distances to the sun, moon, and stars, effectively invented the open space of the cosmos, replacing the idea of a celestial vault. In philosophy textbooks, the Ionian school, Thales, Anaximander, Anaximenes, is often presented as a search for the first principle, arche. For Thales, water. For Anaximander, the aperon. For Anaximenes, air. In this telling, it seems like nonsense, but the point isn't the specific choice, but the process itself. Thales tried to reduce the diversity of phenomena to a single common natural explanation. He probably inherited the idea of the importance of water from mythology, Oceanus as the father of the gods, the waters before the creation of light in Genesis. But his water is ordinary, not divine. His hypotheses, for example, about earthquakes being caused by waves, were naive, but contained a grain of naturalism. Anaximander went further. If everything consists of one thing, how do you explain the diversity? He proposed a mechanism of condensation and rarefaction. Water is condensed air, earth is condensed water. This was a qualitative step forward. Later, the atomists Leucippus and Democritus specified this with the idea of atoms. And today we know that almost all matter consists of three components: electrons, protons, neutrons, and their combinations and density determine all diversity. The Greeks asked the right questions. And what about Anaximander's aporon? The debates about its meaning, boundless or indefinite, are not as important as the idea itself. The essence of the aporon is that it doesn't belong to the substances of our everyday experience. Simplicius writes, Anaximander considers this principle to be neither water nor any of the other so-called elements, but some other infinite nature. Anaximander argues that to explain the world, one must postulate the existence of something natural, but invisible, not directly perceptible. This is the path that all theoretical science would follow. The atoms of Democritus and Dalton, the fields of Faraday and Maxwell, the curved space-time of Einstein, the quarks of Gell-Mann, the quantum fields, all these are theoretical entities, descendants of the aporon. When an antenna repairman says the waves are weak because of a hill, he is using a conceptual judgment that originates with Anaximander's aporon. Let's return to the only surviving fragment of Anaximander. All things arise from one another and disappear into one another, according to necessity. They render justice and pay penalty to one another for their injustice, according to the assessment of time. Here the idea is clearly expressed that the world develops not chaotically, but according to laws, and these laws govern events in time. The form of these laws is not specified. There is only an analogy with justice. But in the very next generation, Pythagoras, born on Samos, not far from Miletus, and probably having met Anaximander, would come to understand the language in which these laws are written, the language of mathematics. This idea would be taken up and developed by Plato, who made it a pillar of his theory of truth. He even tried to interpret the atoms and elements in terms of geometric figures. Although his specific results were unsuccessful, the direction was correct. Kepler, correcting his initial Platonic error, discovered the laws of planetary motion according to the assessment of time, paving the way for Newton. Galileo, discovering the first law of motion, directly referred to Plato. All of Western science is the realization of the project of Anaximander, Pythagoras, and Plato to find the mathematical laws hidden beyond the visible. But the very idea of a law governing nature was born in Miletus, in Anaximander's theory. Thales is traditionally considered one of the 7 sages of Greece. Anaximander was only 11 years younger. It's unknown if they had a formal teacher-student relationship, or if there was a school in Miletus like Plato's Academy. But it's clear that Anaximander was deeply immersed in the problems Thales tackled: the search for the arche, the form of the cosmos, naturalistic explanations. Even Anaximander's disc-shaped Earth is a development of Thales' idea. However, herein perhaps lies Anaximander's most important contribution to culture. The ancient world knew great teachers and their students: Confucius and Mencius, Moses and Joshua, Jesus and Paul, Buddha and Kaundinya. But Mencius did not dispute Confucius. Paul did not criticize Jesus. Anaximander did something new. He absorbed Thales' teaching, but openly criticized it. Thales, the world is made of water. Anaximander, not true. Thales, the earth floats on water. Anaximander, that's not how it is. Thales, earthquakes are from the earth's vibrations in the ocean. Anaximander, no, they're from cracks in the earth. Cicero was baffled. Thales thinks that all things consist of water, but he did not convince Anaximander of this, though he was his countryman and colleague. The Pythagorean school revered the words of Pythagoras, ipse dixit. He himself said it, and that was an unshakable truth. Anaximander opened the third way, to respect the teacher, to build on his achievements, but at the same time to identify and correct his mistakes, improving the understanding of the world. This is exactly how modern science operates. In philosophy textbooks, the Ionian school, Thales, Anaximander, Anaximenes, is often presented as a search for the first principle, arche. For Thales, water. For Anaximander, the aperon. For Anaximenes, air. In this telling, it seems like nonsense, but the point isn't the specific choice, but the process itself. Thales tried to reduce the diversity of phenomena to a single common natural explanation. He probably inherited the idea of the importance of water from mythology, Oceanus as the father of the gods, the waters before the creation of light in Genesis. But his water is ordinary, not divine. His hypotheses, for example, about earthquakes being caused by waves, were naive, but contained a grain of naturalism. Anaximander went further. If everything consists of one thing, how do you explain the diversity? He proposed a mechanism of condensation and rarefaction. Water is condensed air, earth is condensed water. This was a qualitative step forward. Later, the atomists Leucippus and Democritus specified this with the idea of atoms. And today we know that almost all matter consists of three components: electrons, protons, neutrons, and their combinations and density determine all diversity. The Greeks asked the right questions. And what about Anaximander's aperon? The debates about its meaning, boundless or indefinite, are not as important as the idea itself. The essence of the aperon is that it doesn't belong to the substances of our everyday experience. Simplicius writes, Anaximander considers this principle to be neither water nor any of the other so-called elements, but some other infinite nature. Anaximander argues that to explain the world, one must postulate the existence of something natural, but invisible, not directly perceptible. This is the path that all theoretical science would follow. The atoms of Democritus and Dalton, the fields of Faraday and Maxwell, the curved spacetime of Einstein, the quarks of Gell-Mann, the quantum fields, all these are theoretical entities, descendants of the aperon. When an antenna repairman says the waves are weak because of a hill, he is using a conceptual judgment that originates with Anaximander's aperon. Let's return to the only surviving fragment of Anaximander. All things arise from one another and disappear into one another according to necessity. They render justice and pay penalty to one another for their injustice according to the assessment of time. Here the idea is clearly expressed that the world develops not chaotically, but according to laws, and these laws govern events in time. The form of these laws is not specified. There is only an analogy with justice. But in the very next generation, Pythagoras, born on Samos, not far from Miletus, and probably having met Anaximander, would come to understand the language in which these laws are written, the language of mathematics. This idea would be taken up and developed by Plato, who made it a pillar of his theory of truth. He even tried to interpret the atoms and elements in terms of geometric figures. Although his specific results were unsuccessful, the direction was correct. Kepler, correcting his initial Platonic error, discovered the laws of planetary motion according to the assessment of time, paving the way for Newton. Galileo, discovering the first law of motion, directly referred to Plato. All of Western science is the realization of the project of Anaximander, Pythagoras, and Plato to find the mathematical laws hidden beyond the visible. But the very idea of a law governing nature was born in Miletus, in Anaximander's theory. Thales is traditionally considered one of the 7 sages of Greece. Anaximander was only 11 years younger. It's unknown if they had a formal teacher-student relationship, or if there was a school in Miletus like Plato's academy. But it's clear that Anaximander was deeply immersed in the problems Thales tackled: the search for the arche, the form of the cosmos, naturalistic explanations. Even Anaximander's disc-shaped Earth is a development of Thales' idea. However, herein perhaps lies Anaximander's most important contribution to culture. The ancient world knew great teachers and their students: Confucius and Mencius, Moses and Joshua, Jesus and Paul, Buddha and Kaundinya. But Mencius did not dispute Confucius. Paul did not criticize Jesus. Anaximander did something new. He absorbed Thales' teaching but openly criticized it. Thales, the world is made of water. Anaximander, not true. Thales, the earth floats on water. Anaximander, that's not how it is. Thales, earthquakes are from the earth's vibrations in the ocean. Anaximander, no, they're from cracks in the earth. Cicero was baffled. Thales thinks that all things consist of water, but he did not convince Anaximander of this, though he was his countryman and colleague. The Pythagorean school revered the words of Pythagoras, ipse dixit. He himself said it, and that was an unshakable truth. Anaximander opened the third way, to respect the teacher, to build on his achievements, but at the same time to identify and correct his mistakes, improving the understanding of the world. This is exactly how modern science operates. Copernicus did not reject Ptolemy. He studied him deeply, borrowed his methods, and only then, understanding the limitations, radically transformed his system. His On the Revolutions of the Heavenly Spheres is so similar to Ptolemy's Almagest that it seems like a revised edition. Ptolemy was Copernicus's teacher. But Copernicus declared that Ptolemy was wrong about the most fundamental thing, the immobility of the Earth. Einstein had the same relationship with Newton. The power of scientific thinking lies in this continuous questioning, based on recognizing the value of past knowledge. It is said that the scientific revolution did not happen in China precisely because the figure of the teacher was never criticized there. In China, it seems, there was no Anaximander, or if there was, the emperor most likely ordered him to be beheaded. So why did all these fateful intellectual shifts happen, specifically in the 6th century BC, specifically in Greece, specifically in Miletus? 1,000 years before Anaximander, the Mycenaean civilization, 16th to 12th centuries BC, flourished in Greece, with its palaces, demigod kings, complex bureaucracy, and writing system, Linear B, very similar to Mesopotamian cultures. Around 1000 BC, it collapsed, and the Dark Ages began. Greece was reborn in the 8th to 7th centuries BC, re-establishing contacts with the East. A new writing system appeared, the alphabet, borrowed from the Phoenicians. And here the Greeks made another revolution. The Phoenician alphabet was consonantal, only consonants were written. The Greeks, adapting it, used extra Phoenician letters to denote vowels. Thus, the first complete phonetic alphabet was born. Reading and writing became incomparably easier. Writing, previously the domain of a caste of scribes who kept knowledge secret, remember the tablet of secret knowledge from Nineveh threatening curses for disclosure, became accessible to a much wider circle of people. In 7th to 6th century Greece, there were no omnipotent kings, no powerful priestly castes, no sacred texts dictating knowledge. The city-state, the polis, became autonomous, and decisions were made through free discussions among citizens. The process of democracy began. Solon, a contemporary of Anaximander, wrote the first democratic constitution of Athens. The desacralization of power went hand in hand with the desacralization of knowledge. The law that Anaximander sought for the cosmos was akin to the law that citizens sought for the polis. Ancient cosmogonies, the Babylonian Enuma Elish and Hesiod's Theogony, told of an order established by a triumphant god. The Greeks, having exiled their kings, discovered that society could exist and prosper without a king god. They began to seek other ways of understanding the world. To accept democracy is to recognize that the best ideas are born in discussion, that criticism is useful. These same hypotheses lie at the heart of science. The birth of science and democracy have a common origin. Miletus, being a Greek outpost most open to the influences of the ancient Eastern empires, Egypt, Babylonia, and Lydia, became a melting pot. Civilizations thrive by mixing. Herodotus describes how Hecataeus, bragging to the Egyptian priests about his divine ancestor in the 16th generation, was shamed when they showed him 345 statues of human priests who had succeeded one another. This shock from the encounter with antiquity and a different perspective perhaps is what awakened the critical spirit that became the hallmark of the Hellenic mind. As James Shotwell said, it was there that the critical thought of the Western world was born. Did science begin with Anaximander? The question depends on the definition of science. If it's experiment, then Galileo. If it's quantitative models, then Hipparchus and Ptolemy. If it's the investigation of nature, then Anaximander. The choice of a starting point emphasizes a certain aspect of science. Over the last 100 years, our understanding of science has changed, largely due to the collapse of Newtonian physics in the early 20th century. We realized that even the most successful theories can be wrong. Einstein and Heisenberg radically rethought the world. Newton saw empty space and particle pebbles. Einstein showed that space is a flexible sea, and Heisenberg that particles are hybrids of particles and waves. This led to new technologies, but also to confusion. If Newton was wrong, what do we know at all? Some philosophers reduced science to verifiable predictions in limited domains. But then Copernicus discovered nothing, as his system was no more accurate than Ptolemy's, and the sun is not the center of the universe. If Cardinal Bellarmine's view had won, that Copernicus's system was just a calculation, there would be no modern science. Science is not just about predictions. The universe does not revolve around the Earth. Matter is made of protons, electrons, and neutrons. There are billions of galaxies in the universe. Rain is evaporated water. 14 billion years ago, the universe was a ball of fire. We are related to ladybugs. These discoveries have changed our understanding of the world, and their value goes far beyond quantitative predictions. Science is the construction and development of an image of the world, a conceptual framework for thinking about it. It is born of ignorance and challenges the known. It exposes prejudices and creates new tools for thinking. It is a continuous search for a better way to perceive the world, an exploration of new forms of thought. Long before technology, science was visionary. Giordano Bruno's infinite universe paved the way for Galileo. Einstein imagined himself on a beam of light. Karl Popper believed that science consists of theories that can be falsified. Thomas Kuhn spoke of paradigms and scientific revolutions, where an old theory is replaced by a new, often incommensurable one. However, as a scientist, I feel that the connection between theories is missed here. A new theory is not a tabula rasa, but a transformation of existing knowledge. In 1905, when Einstein created the special theory of relativity, he didn't completely reject Galileo, Newton, and Maxwell. He accepted their basic qualitative aspects and, to reconcile them, abandoned the implicit assumption of absolute simultaneity. He changed the rules of the game. Copernicus immersed himself in Ptolemy, retaining his apparatus but discarding the immobility of the Earth. Scientific leaps often occurred not from solving a given problem, but from realizing that the problem was posed incorrectly. Anaximander didn't solve the question of how the heavens move overhead. He understood that the heavens are everywhere. Science is a process that builds on existing theories, but constantly revises them, including the most basic rules of thought. Theories are not absolutely incommensurable. Discoveries are translated into a new language. Ptolemy's Almagest and Copernicus's On the Revolutions are strikingly similar in structure and language, although they paint opposite pictures of the cosmos. It's the same research program. Science is patching the single ship of our thinking, which over time changes beyond recognition. So why is science reliable if it is constantly changing? Because at any given moment, its description of the world is the best available. Its evolutionary nature is the source of its reliability. Scientific answers are not final, but they are the best at the moment because science is open to better answers. Its credibility is based not on certainty, but on a radical absence of certainty. As John Stuart Mill wrote, "The beliefs which we have most warrant for have no safeguard to rest on, but a standing invitation to the whole world to prove them unfounded." We cannot find an absolute foundation for knowledge. Every time we thought we found one, we were wrong. Reality is not a hypothetical final entity, but what we come to know. And we know a lot about it, but it never ceases to amaze us. The awareness of the historical and cultural variability of judgments often leads to radical cultural relativism, the idea that all opinions are equally valid. This is self-contradictory. The concept of truth exists within our discourse, and we cannot abandon it. Cultures are not isolated buckets, but interconnected vessels. They interact and influence each other. Remember the measurement of the sun's altitude by Eratosthenes and Chinese astronomers. Eratosthenes, assuming a spherical Earth, correctly calculated its size. The Chinese, assuming a flat Earth, incorrectly calculated a close distance to the sun. When Matteo Ricci brought Greco-European astronomy to China in the 17th century, Chinese astronomers, comparing the systems, acknowledged the superiority of the Western one. This proves that comparison is possible and makes sense. Radical relativism is ahistorical nonsense. The opposite extreme is the belief in an absolute, infallible truth, usually guarded by religious institutions. But between blind faith and universal relativism lies a third way: dialogue and doubt. True confidence withstands the test of doubt. This requires faith in man and his reason, the very humanism of the Greek cities of the 6th century BC. The question of understanding the world without gods remains. Anaximander, explaining rain by wind and heat and the world by a ball of fire, threw an implicit challenge to religion. Are gods necessary to explain the world? Ancient sources do not indicate his explicit criticism of religion. Thales, according to legend, offered a bull to Zeus, but their theories for explaining the cosmos are expressed exclusively in natural terms, excluding the divine. Saint Augustine wrote of Anaximander, "This philosopher, in his understanding of the creation of the world, attributed nothing to a divine mind. Nothing." The Malaysian way of thinking arose from the preceding culture. Thales' water refers to Babylonian cosmology. But the main thing is in the differences. From the cosmogonies of Thales and Anaximander, the gods disappeared. This was a conflict. Anaximander's successors were persecuted. Anaxagoras was exiled. Socrates was executed. Polytheism somehow coexisted with naturalism, but established monotheism was less tolerant. Christianity, having become the state religion of the Roman Empire, closed philosophical schools and destroyed centers of enlightenment. The great library of Alexandria, the heir of Miletus and Athens, was burned. Hypatia, a philosopher and astronomer, was torn apart by a mob. The knowledge born of Anaximander's audacity survived only in a few codices preserved by the wise men of India, Persia, and the Islamic world. The Enlightenment brought the idea of a peaceful coexistence of reason and religion. But this is a fragile compromise. Religion has difficulty accepting critical thinking as it relies on absolute truths, while science demands doubt in everything. Most people today still believe that God or gods are fundamental to understanding the world. Anaximander did not convince the majority, but his project, a naturalistic understanding of the world, has led to the colossal successes of science. The question he posed is still relevant today. So what is this mytho-religious thinking that is so hard to abandon? Religious activity is possibly as old as language. Roy Rappaport argued that ritual and the sacred are the universal basis for social legitimacy and making sense of the world. Julian Jaynes suggested that the idea of God arose in the Neolithic, when groups became too large for direct control, and the voice of an absent or deceased ruler was introjected, becoming the voice of a god. Marcel Gauchet saw religion as the past general economy of humanity and monotheism as a phase of its decay, leading to the emergence of personal spirituality. Religious thinking is closely tied to the structure of our mental universe and social context. We do not fully understand how our minds work. Consciousness, free will, divinity, perhaps these are just labels for processes whose complexity is beyond our grasp. But this does not mean we should not trust our thinking. Tradition is just the codified thinking of people of the past who knew even less. Anaximander represents a step in liberation from ancient forms of thought. His true discovery was not where rain comes from, but that our conceptions can be wrong. The world is infinitely more complex than our naive images of it. We must choose to hide in empty truths or to accept the radical uncertainty of our knowledge, remaining like the earth, suspended in the void. The second path requires trust in a way of knowing that can admit its mistakes and expand its horizons. In the Rig Veda, an ancient Indian text, there are lines: "Who truly knows? Who here can declare it? Whence it was born? Whence this creation? So who knows whence it came to be? He alone knows, or perhaps he does not know." Anaximander's legacy is immense. He created the investigation of nature, physics, became the first geographer, an evolutionary biologist, a rationalist astronomer. He introduced the idea of a law of nature and of theoretical terms. He founded the critical tradition. He carried out the first scientific revolution, showing that the Earth floats in space and that our pictures of the world can be redrawn. This is the essence of scientific thinking, a constant search for new ways to conceptualize the world, a rebellion against established opinions. This path opened by Anaximander, a path of constant rethinking of the world, is a stunning adventure in which there is something frightening, the need to admit our own ignorance. Accepting uncertainty not only opens up a sublime path for us, but it is also a choice that is honest and beautiful. Our knowledge, like the earth, floats in nothingness. Its impermanence does not deprive life of meaning, but makes it more valuable.